Okay, so today we're going to be starting our next unit, which is all about probability. And probability is a branch of mathematics that describes the pattern of chance outcomes. Probability outcomes are our basis for inference, which, if you'll remember, is what we use if we are trying to make predictions or base conclusions about a particular population. So we call a phenomenon random if individual outcomes are uncertain, but there is a nonetheless regular distribution of outcomes in a large number of repetitions. The law of large numbers says that if we observe more and more repetitions of any chance process, the proportion of times that that specific outcome occurs approaches a single value. We call this value the probability. A good example of what we're trying to say here is using a coin flip, and that's really one of the more simple ways of looking at it. But every time I take a fair coin and I flip it, I don't know what the next outcome is going to be. I don't know if I'm going to get heads or tails for each individual flip. But I do know that overall, there's a 50% chance of getting heads each time and a 50% chance of getting tails each time. And so the idea is if I repeat this process and I keep flipping this coin over and over again, even though I don't know the outcome of each individual flip, I do know that if I repeat the process, I can expect about half of those outcomes to be heads and about half of those outcomes to be tails. So we talked about experiments in the last unit, and an experiment is any sort of activity whose outcome cannot be predicted with certainty. For example, flipping a coin, rolling a die, etc. An outcome is one of the possible things that can occur as the result of an experiment. The probability of an outcome is the number that represents the likelihood of that occurrence happening, of that particular outcome. So that we say that the set of all possible outcomes in a sample space is denoted using a capital S. So everything that could possibly happen in an experiment, we call S, all of the possible outcomes. An event is any collection of those outcomes for some chance process. So that means that an event is a subset, is a smaller set of our sample space, all of the possible outcomes. The theoretical probability of an event is arrived through calculations, whereas the empirical probability is arrived at through observation or simulation. So theoretical probability is what we think will happen based on the odds without actually conducting the experiment. Empirical probability means that we actually went through the process and observed what happened, or perhaps created a simulation to observe what would happen, and we calculate the likeliness based on the actual observations that we've made. So one of the ways that we can define a sample space easily is by using a tree diagram. And a tree diagram is just a way of mapping all of the possible outcomes that we could have during an experiment, our sample space. So if we look at that first example, it says to name the sample space for each of the following. We're going to look at the sample space for one flip of a coin, for two flips of a coin, and for three flips of a coin. So assuming that I have just a regular fair coin, if I flip that coin one time, then I'm going to get one of two possible outcomes. I'm either going to flip heads or I'm going to flip tails. So my sample space, all of my possible outcomes, would be the set containing either a heads or a tails. One of those two things has to be what happens. Now let's say that I flip two coins. I have two possibilities for each of the coins. Each of those coins could get heads or could get tails. So the first coin that I flip is going to have one of two outcomes: heads or tails. But when I flip the second coin, regardless of what outcome I got on the first coin, again, I have two possible outcomes. So let's say that my first coin gives me a heads when I flip it. When I flip the second coin, it could either be heads or tails. And if the first coin flips tails, when I flip the second coin, I could either get heads or I could get tails. So now I actually have four possible outcomes in my sample space. One outcome is that my first coin could flip heads, and my second one could flip heads. So we'll say HH for two heads. Or my first coin could give me a heads, and my second coin could give me tails, so we'll call that HT. Or if my first coin gives me tails, my second coin could give me heads. Or if I get tails for the first one, I could also get tails for the second one. So then again, there are 4 possible outcomes that define the sample space of all of our outcomes for flipping 2 coins. If we extend this idea to 3 coins, again, each one of those coins could be heads or could be tails. So on my first flip, I'm either going to get heads or tails. Regardless of what I get on my first flip, when I flip my second coin, I could get heads or tails. So if I get tails, I could get heads or tails on my second coin. And then regardless of what happened on the first 2 coins, when I flip my third coin, again, I've got 2 possible options. I could get heads or tails for each one, getting a little cramped here, of those outcomes. Heads, tails. So now I see that I have 8 possible outcomes in my sample space. So now my sample space would be that all 3 of the flips give me heads. That's one possibility. Or I could get 2 heads and then tails. Or I could get a heads, a tails, and then a heads. Or I could get heads, tails, tails. Or I could get tails on the first one and get heads on the second 2. Or I could get tails on the first one, heads on the second one, tails on the third one. Or I could get 2 tails and then a heads on the third one. Or finally, all 3 of those coin flips could consist of tails. So we see that we have 8 possible outcomes. And not only does the tree diagram help us see how many possible outcomes we have, but it actually allows us to look at what each of those possible outcomes are. Okay, so let's take a look at the next example. We're going to make a tree diagram for this one as well. It says that suppose a new area code is being created. The first digit must be either a 4 or a 5. The second digit must be an 8 or a 9. And the last digit could be either a 3, a 4, or a 5. How many area codes are possible? So I'm going to start with my first digit. And it says that I have 2 possible numbers for my first digit. So my first digit has to be either a 4 or a 5. Then if I look at the possible outcomes for the second digit, it has to be either an 8 or a 9. So if I have a 4, my second digit could be either an 8 or a 9. And if I have 5 as my first digit, I could have either an 8 or a 9 as the second digit. And then finally, it tells us that the last digit could be either a 3, a 4, or a 5. So then for each one of these combinations that we have of the first 2 digits, my third digit could be either a 3, a 4, or a 5. So I could have a 3, 4, or 5 on this branch, a 3, a 4, or a 5 on this branch, 3, 4, or 5 here. And then for my last one, I could have 3, or 4, or 5. So we have 3, 6, 9, 12 possible outcomes. So 12 possible area codes. Notice that if I were to take the number of each outcomes and multiply them together, I would end up with 12. So I have 2 possible outcomes for my first digit, 2. I have 2 possible outcomes for my second digit, 2. So that 2 times 2 gives me the 4 possible outcomes for the first 2 digits. And then for the third digit, I have 3 possible outcomes. So if I multiply the two arrangements of the first, the 2 for the second, and the 3 for the third, I would get the same result. I would get that there are 12 possible area codes. But again, the tree diagram allows us to see what all of those possible area codes are. For example, I can see that 484 is a possibility, or 485 is a possibility, or 583 is a possibility. So not only do I know the total number of possible area codes for my tree diagram, I can actually see what each of those would be. That's one of the advantages of a tree diagram, is we can actually look and see what all of the possible outcomes are. However, the disadvantage of a tree diagram is if we have lots of possibilities or lots of different combinations that we're creating, we can see how a tree diagram would get really big and kind of complicated really fast. So what we're going to do is we're going to look at some basic probability rules that will allow us to do some of these calculations a little bit faster when we don't need to actually see what the outcomes are. We just need to know what the possible number of outcomes is going to be. So some basic probability rules that you need to be familiar with. First off, all of the possible outcomes have to have a combined probability of 1. If I'm looking at every possible outcome, the probability of one of those outcomes happening has to be 100%. So that's what we mean when we say that the combined probability has to be 1. Also, for any event A, the probability of that event has to be greater than or equal to 0 and less than or equal to 1. Specifically, if we're saying that the probability is equal to 0, we're saying that it will never happen. There is a 0% chance of that event occurring. If we say that a probability is equal to 1, then we're saying that it's certain to happen. It will always happen. So our probability has to be somewhere between never going to happen and certain to happen. The closer the probability is to 0, the less likely it is to occur. And the closer the probability is to 1, the more likely it is to occur. So to calculate the probability for any one specific event, we would take the total number of outcomes that correspond to event A and divide it by the total number of outcomes in the sample space. So how many ways could A happen, and how many possible outcomes are there? And again, this is why a tree diagram can be really important. If we're calculating the probability of an event A, we need to know the number of ways that A could occur, and our tree diagram could help show us that. But we also need to know the total number of outcomes, and our tree diagram shows us that as well. So the tree diagram can be very useful in calculating the probability of a single event. The complement of an event A is the event that A does not occur. So we call A complement the event that A doesn't happen. We denote it using this notation A of C, or sometimes we'll call it A prime. That little mark is we read as a prime. A sample space S can be represented by the following Venn diagram. So if this box represents S, all of the possible outcomes, and our circle here represents event A, an event is either in A or it's not in A. So we can use the probability of A or A complement to help us figure out the probability of an event of the other. Because we know that the probability that S happens, all of our possible outcomes, is always going to have a total probability of 1. So if S is all of our outcomes, the probability of getting an outcome is 100%, is 1. And since our sample space S is made up of either A or A complement, it either happens or it doesn't, that means that the sum of A and A complement represents all of the possible outcomes. It either happens or it doesn't. So A plus A complement then would be our total sample space. Which means that if I take the probability of A happening and I add the probability of A not happening, then I get the probability of S, which again would just be 1. And so if I manipulate that If I want to know the probability of A not happening, all I would have to do is take 1 and subtract the probability that A does happen. And this can be a really powerful tool because sometimes when we're calculating probability, it's easier to find the chance that something does happen or doesn't happen than it is to find the other. So if we can find one of these easier than the other, then we can find the other simply by subtracting from 1. Okay, so the fundamental counting principle was kind of what we were applying on that last example on the first page. The fundamental counting principle says that if there are m different choices for decision 1 and n different choices for decision 2, then the first and second decisions together can be taken m times n ways. So in other words, if event 1 can happen m ways and event 2 can happen n ways, then the combination of those would just be m times n. So for example, let's say you know the first 3 digits of a 7-digit phone number. You know that the 4th digit is not 0, and you know that the last digit is an odd number. What are the total number of telephone numbers that hold these conditions? So we know the first 3 digits, but we're not sure what the last 4 digits are. So what I'm going to do is I'm going to put a mark for each of the 4 digits. We have 4 mystery digits at the end of our telephone number. We know that the 4th digit here, oh no, the 4th digit would be here, because we know the first 3. So this is digit 4, digit 5, digit 6, and digit 7. We know that the 4th digit is not 0. Well, that means that there are 9 different numbers that the 4th digit could be, 1 through 9, anything but 0. So there are 9 different possibilities for digit 4. We also know that the last digit is an odd number. So that means that there are 5 different possibilities for the last number, 1, 3, 5, 7, or 9. So there are 5 possible digits that could be in the last place. They don't give us any information about digit 5 or digit 6, which means that there are 10 possibilities for digit 5. We've got 1 through 9, or it could be a 0. And we've got 10 possible digits for digit 6. So if I want to know the total number of telephone numbers that hold these conditions, that would be 9 times 10 times 10 times 5. That's the number of different combinations that we could create based on the number of outcomes for each of those digits. So there are 4,500 different combinations of numbers that we could have that would fit that criteria, which means that if we're trying to guess what that number is, the odds of us guessing correctly are not looking very good because there's 4,500 different ways, different combinations that we could have anything but a 0 here and an odd number here. So if 2 events, A and B, have no outcomes in common, then we say that those events are mutually exclusive or disjoint. Those 2 words mean the same thing, and we use them interchangeably. What we're saying is that if something happens in A or happens to fall in A, then it won't be in B. Or if something happens to fall in B, then it won't be in A. So you're either in A or you're in B, but you can't be in both. And that's what mutually exclusive or disjoint means. So if we know 2 events are mutually exclusive, then to calculate the probability of being in either A or B, we can use the addition rule for disjoint events. So if A and B have no outcomes in common, then the probability of being in either A or B is simply the probability of being in A plus the probability of being NB. Again, this is only true for disjoint events, only if we know they have no outcomes in common. If they do have outcomes in common, then we're not going to be able to use this. We're going to have to adjust this rule a little bit to find the probability of A or B happening, and we'll look at that rule later on. So in our last example, it says that for women between the age of 25 and 29, the probability that they have never been married is 0.353. The probability that they have married is 0.574. The probability, or that they are married, is 0.574. The probability that they are widowed is 0.002. And the probability that they are divorced is 0.071. So these women either fall into one or the other of these categories. Either you've never been married, you're currently married, you're widowed, or you're divorced, and you're classifying yourself as one of these four things, which means that these are mutually exclusive. These are disjoint, because you can't have never married and be divorced at the same time. Or you can't be married, consider yourself both married and divorced at the same time. So if we wanted to calculate the probability that a woman between the ages of 25 and 29 has never married or is divorced, never married or divorced, then the probability of never being married or being divorced is just going to be the probability that you have never married plus the probability that you're divorced. Because those events are mutually exclusive. You can't be divorced if you've never married. So you're either one or the other, but you could not possibly be both. So the probability of never being married is 0.353. The probability of never being divorced, or having been divorced, is 0.071. So the probability that if we randomly select a woman between the ages of 25 and 29, that she'll have either never been married or be divorced would be those sums, which would be 0.424. In other words, we're saying that about 42.4% of women between the age of 25 and 29 are never married or have been divorced.